This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2018 AP Calculus exam, free response question AB5. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on or I'll highlight the solutions presented in these guidelines, not how the points were awarded. This question was not calculator active. However, I'll show you how to use technology to explore and answer parts of this question and to confirm solutions, where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. This problem initially involves a function f, defined by e to the x times the cosine of x. In part A, we need to find the average rate of change of f on the interval 0 to pi. In part B, we need to find the slope of the tangent line to the graph of f at x equals 3 pi over 2. In part C, we need to find the absolute minimum value of f over the interval 0 to 2 pi. And in part D, a new function g is introduced. We know that g is differentiable. We have the value of g at x equals pi over 2, and the graph of g prime is given. We need to use all of this information to evaluate the limit of a quotient. Part A was worth 1 point, simply for the answer. However, the supporting work presented must be correct. For example, if there's a linkage error or a presentation error, the student would not earn the point, even in the presence of the correct answer. Part B was worth 2 points. The first point was for finding a general expression for the derivative of f. And the second point was for evaluating this derivative at x equals 3 pi over 2 to find the required slope. Note that the question did not ask for an explicit expression for f prime of x, and therefore the student is not obligated to present f prime of x. It is possible, and some students did this, to start and complete the problem by writing an expression for f prime of 3 pi over 2. Part C was worth 3 points. The first point was a conceptual point for knowing and writing f prime of x equals 0. The second point was for identifying the two critical values, in this case, two values where f prime of x equals 0, as candidates for x coordinates where the absolute minimum value occurs. And the third point was for finding the absolute minimum value and providing sufficient justification for the answer. The justification here is the table of values. Part D was worth 3 points. The first point was for recognizing and then stating that g is continuous at x equals pi over 2, and for confirming that both the limit of the numerator and the limit of the denominator are 0. We need to know that g is continuous in order to compute this limit by direct substitution. The second point was for applying L'Hopital's rule, which in this problem means taking the limit of the quotient f prime of x over g prime of x. And the third point was for the final answer. Note that the student could earn a maximum of 1 out of 3 points in Part D if they did not sufficiently communicate L'Hopital's rule by writing the limit of a ratio of the derivatives. In Part A, to find the average rate of change of f on the interval 0 to pi, we need to consider this difference quotient, and then evaluate the function f at pi and 0. Well, this is pretty straightforward using the TI-Nspire. I defined the function f, and then I simply computed the difference quotient. Note that since I'm using a CAS version, I have the exact symbolic answer. That's pretty cool. In part B, we need the slope of the tangent line at x equals 3 pi over 2. Well, here's the answer presented in the scoring guidelines. If we're solving this problem without technology, a reasonable first step is to find f prime of x, and then evaluate this function at x equals 3 pi over 2. Now, using technology, remember I already defined the function f. Although I don't have to, I can find the symbolic expression for f prime of x. I can actually find the slope of the tangent line in one step. And again, I have the exact symbolic answer. In part C, we need to find the absolute minimum value of the function f over the interval 0 to 2 pi. Using technology, I started by finding the critical values. Well, those places where the first derivative is 0. There are no values where the first derivative does not exist. Then, on a lists and spreadsheet page, I created a table of values. Notice that in column B I have the exact symbolic values of f. Now, all of these values except 1 are greater than 0. So it's pretty straightforward to select the absolute minimum value. However, I created an additional column just so I could see the numerical approximation of each value. Here is some graphical confirmation of the solution to part C. This is a graph of the function f over a little expanded interval. I used the Analyze Graph feature to find the absolute minimum value. This visualization and numerical approximation is confirmation to me that I solved the problem correctly analytically. In part D, there really isn't much I can do to solve this problem using technology. However, let me make an additional assumption and show you how we can at least confirm this solution numerically. Consider the graph of g prime given in the problem. Now, we can figure out the equation of the straight line segment, but the curved segment is a little trickier. So I assumed it was part of a parabola, and I found an equation of best fit. Then I defined the function g prime piecewise. And here's a graph of my function g prime. It's pretty close to the one given in the problem. On a calculator page, I defined the function g. Now, I don't need the 0 out in front, but this demonstrates the net change theorem and the use of the initial condition. And I found the numerical approximation to my analytical limit. On a graphs page, I sketched the quotient f over g, and then I traced close to pi over 2. I feel pretty confident that my analytical answer is correct. At the bottom of this slide is an extension to this problem. Remember, we're given the graph of g prime and an initial condition. Sketch a graph of the function g without using technology. In example 2, I'd like to consider some similar questions as in the free response question, but this time with technology. Consider the function f on the interval 1 to 10. Find the slope of the tangent line at x equals 2. Find the absolute minimum value and absolute maximum value of f. Find the intervals on which f is concave up or concave down. And find the inflection points on the graph of f. I'm going to solve part A and leave the rest for you. On a calculator page, I defined the function f, and then I simply evaluated the derivative at x equals 2. And here's a visualization of this answer. I sketched a graph of f and the tangent line at x equals 2. I can see the slope of the tangent line agrees with my answer on the calculator page. This free response question included a limit problem in which we needed to apply L'Hopital's rule. So here's another limit of a quotient. You might first consider why this has to be a one-sided limit. And here's one more example in which you'll need to use L'Hopital's rule, and some other calculus ideas. The function f is a polynomial, and g is a differentiable function such that g of 0 is equal to 1. The graph of the derivative of g is given, and it consists of two line segments and a semicircle. Use all of this information to evaluate the limit as x goes to 2 of f of x divided by g of x minus x squared. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions, and of how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. I think this problem presents some good opportunities to discuss the importance of proper mathematical notation and how to analyze a function. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.